Okay. All right. Hello, everyone. Ang plano ko na lang ngayon is that I will release a really long video or either a video in two parts. I'm not sure which one. Just a video or videos with all of the other solutions for all of the 8 questions here in steady flow devices. Right? So, ang mangyayari is that even though I'm going to discuss some of this in class on next Tuesday, so March 18, right? Even though I'm going to discuss some of those questions here, I will have them all now para okay tayo. Right? Right? And also, this is just a way for you to also just try pause right now, right? Try to solve it and see if same tayo ng sagot. Okay? Let's see if we have the same answers for this one. Again, full disclaimer, I'm not feeling 100%. So if I sound nasal, I apologize. You will hear some of that. So, all right, let's begin. Refrigerant 134A is compressed at steady state from a saturated vapor at 0.12 MPa, exiting at 1.2 MPa and 70 degrees Celsius with a mass flow rate of 0.108 kilograms per second. Inevitably, heat is lost to the surroundings at a rate of 320 joules every second. How much power should we provide the compressor? Right? Okay. Sorry, you'll also hear some of that. Okay. So now let's just try and annotate everything here. Right? Let's annotate everything. Refrigerant 134A, of course, our substance is compressed. Okay, at steady state from a saturated vapor at 0.12 MPa, exiting at 1.20 MPa and 70 degrees Celsius with a mass flow rate of 1.08. Inevitably, heat is lost. Okay, so that gives us a clue as to how or what the sign is for our Q later on. Heat is lost to the surroundings at a rate of 320 joules every second. And now let's go on into the numerical bits, right? Numerical, numerical, and then the mass flow rate of 0.108 kilograms per second, a rate of 320 joules every second, and basically for the last one, how much power should we provide the compressor, right? So basically what they're asking for here is compressor power. So let's begin, right? Number 3, we will have a compressor, right? So a compressor, again, is drawn like this. Basically, you have your initial state, which is larger, right? Which has a larger, what do you call this? Has a larger cross section, as you can see here, right? And then it becomes thinner, right? So this is a compressor. It compressed whatever fluid was inside, right? And so that's our, I think that's the explanation for why the compressor is like that. But anyway, right, this is our state 1. They said that this is a saturated vapor at 0.12 MPa, right? So we can say now that our P1, right, our P1 is 0.12 MPa, or let's do mise en place, right? That will be, because I know, right, this is R134A, by the way, right? I know that I'm going to have to find this, find properties in the table, right? Because it's one of the five substances that has corresponding saturation and superheated vapor tables. I probably should turn this into bar. 0.12 MPa, that corresponds to 120 kilopascals, which is just the same as 1.2 bar, right? On the other hand, we will have your pressure 2, which is now 1.2 MPa. Look at that. The pressure increased, which is, in fact, indicative that this is a compressor, right? Which now turns into 1,200 kPa, or let's just say 12 bar. And they also say that your temperature 2 is, what is that, 70 degrees? Yes, 70 degrees Celsius. And the mass flow rate here is going to be a solid 0.108 kilograms per second. So for this, for number 3, I will have full units on, right? I will have full units on. And what we just want, right, what is required here is the compressor power. How much work do we need to put, right? Also, right? There is heat being lost to the surroundings at a rate of 320 joules per second. So what is that exactly, right? It's heat, right? It's heat being lost. Therefore, it's negative. So your Q here is negative 320 joules per second, right? Every second, 320 joules is being lost to the environment through heat, through waste heat. And as a result, if you remember, what is a joule per second? A joule per second is just a watt. And so let's try and mold this. Let's try and mold this because we actually don't use watts, right? For the first law of thermo equation, we use most likely kilowatts, right? Kilowatts, 0.32 kilowatts. That is a better kind of expression. And also, let's not forget that this should be negative because it's flowing out. Okay? And so now we can actually just go directly to the first law, right? Q minus W is equal to delta KE plus delta PE. This is an open system now, so we say delta H. And again, actually, all of this should have dots, right? All of this should have dots. Even this should have a dot because we're dealing with mass flow rate, right? So now I will ask you guys, right? I will ask you through the screen, right? Is there any mention of not any mention of a cough, but is there any mention of a speed or an altitude? If there is none, then we can just cross these guys off, right? And so what will happen is that we will reduce this to our more base equation. Q minus W is just your change in enthalpy. And well, your change in enthalpy, where will that come from? That will just be equal to a change in specific enthalpy, right? H2 minus H1. The thing about this now is that we have a value of Q dot. We just found that out earlier. And we have a value of M dot. Do we have values of H2 and H1? Not yet, but because we know it's a saturated vapor at this certain pressure, we can find the value of H1, right? And because we know two things about this refrigerant, now we can also tell that, oh, probably we can get the value of H2 as well, so long as it's superheated vapor, right? So technically, we can find these values together. So we can find them. These are magnifying glasses. And now this is what we need to solve. So if we do find everything out here, we can solve for our value of W for our compressor work. Now let's go ahead and actually find them, right? So first of all, we have a saturated vapor at 1.2 bar. Saturated vapor at 1.2 bar. Let's go now to the R134A tables. This is refrigerant 22. Yan, 134A at the particular pressure, which is 1.2 bar. There you go. So now, what do we actually need? We need the value of Hg, right? Hg, because this is a saturated vapor we're talking about, right? So that will be 233.86. Right, 233.86. This will just be, Hg at 1.2 bar, which is 233.86 kilojoules per kilogram, right? And now let's try and look and hope, right, that because we're given pressure and temperature, we are going to get a superheated vapor, hopefully. It does look like a superheated vapor to me. 1.2 MPa is a lot of pressure. So let's just see, 1.2 MPa, so that corresponds to 12 bar. Hopefully there is a 12 bar. There is a 12 bar. There you go, 1.2 MPa. And let's see, 70 degrees is counted. So we have the value here. And if you guys don't want to continue just like scrolling up and down, if ever you do have a digital copy, you just have to remember VUHS. So in this case, what you're trying to get here is H, right? This one, 298.96, right? 298.96. So there you go, 298.96 kilojoules per kilogram. Now we have everything we need. We can now just plug everything in. Negative 0.32 kW, kilowatts, right? Minus your work, compressor work, And then what is your M in here? It's 0.108 kilograms per second. And then your H2 is 298.96 minus, right, 233.86. I still don't have my calculator. It's in there somewhere, right? And then we cancel the kilograms. I will cough. Don't stay up all night, please. And this kilojoules per second will cancel out, giving us a kilowatt. So everything in here is in terms of kilowatts. So we don't actually need to worry about the units. We know that your W in here should be in terms of kilowatts. So if we solve for W either by, I don't know, by shift solve or what have you, right? I will prefer to do this algebraically so that I can stall for some time, right? I will move this W here so that it becomes positive. I will move everything here so that it becomes negative, right? And we will have negative 0.32 minus 0.108 times 298.96 minus 233.86, right? 233.86. And I will just plug this into my calculator, my phone. Let's see. Negative 0.32 minus 0.108 times 298.96 minus 233.86. That gives us a total of negative 7.3508. Negative 7.3508. Let's just simplify that to 2 decimal places. That gives us negative 7.35 kilowatts. This is our answer. Right? That's our answer. So very good. That didn't take us a lot of time. This is our solution. Right? And the thing about this nga is that you're supposed to be able to quickly ascertain, oh, I need to do this. Right? Your foundation, aka your quiz 1, should be able to tell you, oh, because you know it's a saturated vapor at this particular pressure, you should be able to get every other property out there, so long as it is one of the 5 substances: water, R22, R134A, propane, and ammonia, right? So if you don't have that, kind of like instant or fast recall, it's time for you to, restudy, right? Review. That's the better term. Review your what do you call this? Your quiz 1 topics, right? Your quiz 1, yeah, your quiz 1 is with you, so maybe you can get it from there. And then this one, right? The second quiz is all about the first law, right? Albeit for closed systems, but this should still apply, right? For the first law, you should be able to just write this down seamlessly and identify which terms are not usable. Like for example, KE and PE are gone because there are no specified changes in speed or altitude, right? You should be able to also tell if heat is going out, it should be negative, right? And also, near the end, you should be able to tell yourself, okay, this looks okay because your compressor power should be negative, right? Your work should go in, right? Your work should go in, right? Your work should go in. There you go. So it all comes together for quiz 3, right? And mind you, if you think you've done this quite quickly, then that's good, right? If you've done this quite quickly, then that's good, because I will tell you for topic 6, we will do this over and over and over and over again, right? Okay, let's now move on to question number 4. Let's move on to question number 4. A pump. This one, right? A pump is used to carry water flowing at a rate of 1.5 kilograms per second up to a reservoir 15 meters above the suction side, right? A pump has 2 sides: a suction, right? The one where it sucks fluid in, and then discharge, the discharge side where it spits it out, right? Which has a pressure of 3 bar absolute, right? Suppose atmospheric pressure is 1 bar, right? If the water, oh, there's no space in here. If the water temperature remains constant at 25 degrees Celsius and that the changes in kinetic energy are negligible, how much power should we provide the compressor? Again, right? A pump and compressor here, interchangeable. So this should be pump actually, but oops. Now let's start with the details. A pump, right? This should give us enough info to be like, okay, I know what the context is supposed to be, right? A pump is used to carry water flowing at a rate of 1.5 kilograms per second up to a reservoir 15 meters, a reservoir 15 meters above the suction side, right? Which is a pressure of 3 bar absolute. If the water temperature remains constant at 25 degrees Celsius and that the changes in kinetic energy are negligible, how much power should we provide the compressor? Again, let's just go ahead and do the red now. How much power compressor? And the thing about this now is that this question is sending us different signals. It's sending us mixed signals, right? A rate of 1.5 kilograms per second. I will expound later. 15 meters above the suction side, which is a pressure of 3 bar absolute. Suppose atmospheric pressure is 1 bar. If the water temperature remains constant at 25 degrees Celsius and that the changes in kinetic energy are negligible, this is our full annotated question, right? And I suppose it would be better, and it would be much better if we have a good figure, right? Because, well, this kind of thing is very confusing, for the lack of a better term, right? Let's go now with number 4. Let's separate away from that, and let's just have this figure, right? Let's just have this figure where, let's say this is the pond or something, right? And then this is the pump. The pump is usually drawn like this, right? You have a pump, right? And then this is the discharge side. So the discharge side, right? Actually, let's just draw this outside, right? So for you to draw a compressor, you already know that trapezoid shape. For the pump, you have a discharge side, right? That is where the fluid will come out with more energy. And then usually the intake side or the suction side, intake or suction, is on this side. And it goes directly to the center of the pump. And I will cough. Okay. And usually this pump is grounded, as in like it's bolted to the ground. The thing is, if you've heard pumps before or compressors before, they're quite noisy and they vibrate and they rattle a lot. That's why they are mounted to the ground, right? Something like that. So this is quite already what do you call this? This is already quite a complicated picture. You can just do this, and then this. That's okay. That's good enough, right? But suppose we have this reservoir here, up here, right? Actually, we have a tank. I remember, I'm just getting this from the book. You guys can see, actually, this is also in the Moran and Shapiro book. The same thing that was, what do you call this? The same thing where I got the steam tables from, or we're getting the steam tables from. So, they said the water is flowing at a rate of 1.5 kilograms per second. There you go. 1.5 kilograms per second. Hopefully, this is obviously water, right? But let's just still put it there. And then a reservoir 15 meters above the suction side. Let's just say that the suction side is coming in. Let's say here's the pump, right? And then the suction side is coming in from here. And then the discharge side is coming from above. And then there you go. And then this is our discharge and this is our suction. And let's just say their difference is 15 meters. Right? Their difference is, there you go. Yeah, their difference is 15 meters. Okay? The pressure of this reservoir, the pressure of this state 2, let's just say, is 3 bar. And they said that right? Well, they said that this needs to be at atmospheric pressure, right? You're sucking in water from atmospheric pressure. That means that this P1 is going to be 1 bar. And they also said that the temperature, or the water temperature remains constant at 25 degrees. So T1 is T2, which is 25 degrees. Now, the thing about this is that if you see that, you might be tempted to say, oh, that's an isothermal, right? That's an isothermal compression that's happening. And so you might be tempted to bust out, oh, P1, V1, ln V2 over V1, right? But the thing about this is that, well, pumps are supposed to be isentropic. The thing about this is that they are just saying that the water remains water, right? It doesn't get compressed anymore. It doesn't turn into a superheated vapor kind of thing, right? Just unlike this one, right? This one, right? This was saturated vapor, and then you compress it, boom, it becomes superheated, right? This just becomes water. It's just water still, right? And so what happens now is that we need to understand this is a pump we are using, right? And pumps usually are isentropic, but when you're dealing with liquid, you should instead think of this pump as being isometric. So even though, where should I say this? Right? Right? Even though T1 is equal to T2, basically a way for us to say that this is isothermal-ish, right? This is still basically, for us, an isometric operation, right? The pump is still approximated, as isometric, as isometric, right? As isometric. There you go. And now, well, there's only one thing that remains, which is, what do we need? We need, right? We need power, right? The compressor power. Oops. We need compressor power. And so now, what's going to happen, right? The thing about this is that, again, right? In this case, there's so many unknowns, right? For example, let's just write down even just the first law, right? Q minus W, change in KE, change in PE, and change in H. The thing about this is that, well, you don't know how much heat is being transferred, let alone if there is any heat that is being transferred. But let's just remember, I grounded the pump, by the way. Let's just remember, what is the pump supposed to, what is the ideal process of this pump? The ideal process of the pump is isentropic, or adiabatic, shall we say. Both of those processes describe no heat transfer. No heat transfer. Right? Okay? Okay? And now, what about kinetic energy? They say it's a, what do you call this? There are no changes in kinetic energy, right? Changes in kinetic energy are negligible. And the thing about this is that, what about the other things now? What about the other things now? Well, what about potential energy? There clearly is a change in elevation, so we can't just, excuse me, we can't just remove that. And what about enthalpy? This is the big thing now, right? For all intents and purposes, if you look at water, right? Water, if you guys don't believe me, right? At 1 bar, the saturation temperature for water is 99.63. The temperature here is 25. It doesn't matter if you go 3 bar, it actually increases. The saturation temperature actually increases. Both of these things, both of these states are compressed liquid. So you might be tempted to say, okay, sige, let's just get the HF. But no, it's not supposed to be like that. Right? It's not supposed to be like that. What's actually supposed to happen is that you're supposed to look at, right? You're supposed to look at it this way. Okay? And this is gonna be the very weird kind of thing, right? Let's just put these now, right? Change in PE. And then because we say, right, because we say that H is equal to U plus PV, right? H is equal to U plus PV, what will happen is that a change in H is supposed to be a change in U plus a change in PV, right? So let me just, yeah, there you go. So that is completely clear. It's a change in PV, a change in flow energy. Now, this is where this note comes into play, right? Even though it sounds isothermal, the pump is approximated as isometric. So it sounds like the pump is supposed to be isentropic, but then it's approximated as isometric, even though it looks isothermal. So it's very confusing, right? So I'm taking this step by step, right? When we say that your T1 is your T2, right? When we say that things are isothermal, it seems like, oh, okay, there's no change in internal energy. If we remember, right, internal energy is just a function of temperature, aka the internal energy is how jiggly or how fast the molecules in your fluid are jiggling. If they are jiggling the same based on the temperature, well, there's going to be no change in your U. So that means 0. So I will just give this note here. And basically, your delta H now becomes your change in PV, but we said that it's isometric. We said that your volume remains the same. We said that your volume remains the same. So if you put this out, let's say if you expand this, right? If you expand, actually, we just put it here. P2V2 minus P1V1, your V's are the same. And therefore, you can just group them out and say that your V, P2, P1. And if you put all of the flow rates in, there should be a dot, oh, sorry, this should be a slash and slash. That is your equation for enthalpy. Right? That is your equation for enthalpy. Right? Your change in enthalpy should be plus V slash times P2 minus P1. And if you're thinking now, which V slash? Because the thing is, well, this has a certain value of V, right? And this also has a certain value of V, but actually, no, they are the same. If you remember, right, we both states here, both state 1 and state 2 are compressed liquid, right? We said this earlier, we just checked, right? And how do you get the approximate specific volume? The approximate specific volume is just checking VF at the temperature at 25 degrees. So at this rate, V2 is also your VF at the same temperature, which is 25 degrees. So actually, they both just have the same value of V, which in this case will be, let's just look now. Pressure, temperature, this one is 25. So your VF is 1.0029, and then, please don't forget, divide by 1,000. 1.0029 divided by 1,000. This is meter cube per kilogram. And now we can put everything together because this can just be expanded to look like, right, M dot V and then P2 minus P1, right? This is the same thing that I have said earlier. Where is this thing? There you go, right? There you go. Where were we? There you go. And now we have this, right? And how do we expand? Oh, I forgot to expand potential energy, right? How do you expand that? Well, that's just going to be mgz2 minus mgz1, right? And actually, both of these should have flow rates. But then again, if you guys remember from our earlier discussion, we said that, oh, these guys have their units in terms of watts. But these guys have their units in terms of kilowatts. So it would be better if we just divided all of this already by 1,000. Right? And so that's what we'll do specifically. right? And right now, I feel like it would be best if I put in all of the units, right? So this would be, if you remember, if you saw earlier, right, mgz2 minus mgz1 all over 1000. Both of them, both terms here have m dot times g and the over 1000. So I might as well just remove those and put them into here. mg over 1000 times z2 minus z1 plus m dot v p2 minus p1. And now let's fill all of this in. Right? Let's fill all of this in. Is this enough space kaya? Let's just put it here, down here. Your negative work is going to be equal to m dot. So your m dot is what again? 1.5. 1.5 kilograms per second. And then your g is, of course, nothing else is given, 9.81. And then meter per second squared all over 1000. This is for us to turn this into a kilowatt. And then your z2 times z1, well, where is your reference? Right? In here, you usually have a reference. It doesn't matter where your reference is because Z2, or rather your state 2, is higher than your state 1. By how much? By 15. So if you put your reference here, let's say you put your reference here, right? In this case, your Z1 is going to be 0. And then your Z2 is going to be 15 meters, right? If you put your reference, I don't know, here on top, your Z2 will be 0, but because your Z1 is now lower than your reference, it's going to be negative 15. And in either case, all the first law wants is a difference, a change. And how much is the change? Well, it's 15 minus 0. So that's all we need, right? 15 meters. Actually, I'll just put the M in. There you go. And now, let's try and see all of the units here come together. Kilogram per second, meter per second squared, and then meter. So we have here kilogram meter per second squared. If you guys remember, again, this is from Newton's second law. Mass times acceleration gives you a force, a Newton. Right? A Newton meter, that gives you a joule. A joule per second gives you a watt. But because of this over 1000, all of this becomes a kilowatt. Next, we have here our M again. Sorry, I was caught up with the M from before. 1.5 kilograms per second. And then your V, it doesn't matter what your V is, right? 1.00, what was that again? 1.0029, is that right? Yeah, 1.0029 over 1000, right? Meter cube per kilogram. Cancel, right? And now your P2 minus P1, please remember, okay, I will add another note here. Pressures should be in kPa absolute, right? Please do remember this, because if you do just 3 minus 1, sad. That's immediately wrong, right? So this 1 bar and 3 bar, you can actually mise en place to become 100 kPa absolute. And this, you can mise en place to become 300 kPa absolute, right? And so this just becomes 300 minus 100 kPa. Why does this matter so much? Because look, meter cubed kPa. If you remember, combining them should give you a kilojoule. And then if you combine it with the second, you get kilowatts as well. And so once you put everything together, right, we will have negative W will be equal to, let me just put all of this together, 1.5 times 9.81 all over 1000. Again, I'm stalling because like I just want more time. It's not like I'm getting any AdSense from this anyway. Times 1.5 plus 1.5 times 1.0029 all over 1000 times 300 minus 100, and all of this should be in kilowatts. So I'm going to put this now in our calculator. 1.5 times 9.81 all over 1,000 times 15 plus 1.5 times 1.0029 divided by 1,000 times 300 minus 100. That gives us a total. That gives us a total of, right, 0.521. 595 or just 522, I guess, kilowatts. Therefore, if we put it into two decimal places, we will have your compressor work is 0.52, or sorry, negative 0.52 kilowatts. This is how much power you need to input into the pump for it to work properly. Okay? Again, if I do post this and you guys have questions, please let me know. Okay? Either through I don't know, will I like put this in YouTube or something kaya? I'm not sure. But like you can just send me a question, Canvas, Gmail, I guess, right? That's completely fine. But there you go. That is your negative 0.52 kilowatts. This is actually small. This is a small pump. Okay. Anyway. Next, steam. All right, there you go. Steam enters a steady state turbine. Okay, turbine this time around at a pressure and temperature of 30 bar, 360 degrees Celsius, leaving as a saturated vapor at 8 kilopascals. That is a drop. That is a pressure drop. It is known that the turbine develops, oh, that's why, 8.95 megawatts, right? Megawatts. And that the heat leaks out of the turbine at a rate of 0.586 megawatt. That is a lot of heat loss. 0.586 megawatts. Neglecting kinetic and potential energy changes, how much steam was flowing into the turbine in cubic meters per second? Flowing into. Okay? All right, let's begin. Our details are, of course, steam, steady state turbine at a pressure and temperature, leaving as a saturated vapor at 8 kPa. It is known that the turbine develops 8.95 megawatts and that heat leaks out of the turbine at a rate of 0.586 megawatts. Neglecting kinetic and potential energy changes, that is what we like to hear, right? How much steam was flowing into? That is a very important thing to remember, into the turbine. How much steam was flowing into the turbine in cubic meters per second? This is particularly important because usually when I ask how much blah blah blah, it's usually in mass flow rate, right? Or usually in mass, right? Now we look at the numbers, a pressure and temperature of 30 bar, 360 degrees Celsius, leaving as a saturated vapor at 8 kilopascals. It's known that the turbine develops 8.95 megawatts at a rate of 0.586 megawatts. So that's everything. Now we can get into our actual problem, right? So for number 5, what will happen is that we will have a turbine, right? And the thing with turbines now is that they are just the, how do I say this? The opposite? Is that fair to say? That's the opposite of a compressor, right? If what a compressor does is that it compresses something, a turbine's byproduct, right? A turbine's goal is to get energy. But how does it get energy from a fluid? What happens is that it expands the fluid, right? Because you're getting energy from the fluid, what happens is that the fluid cannot contain, or rather cannot maintain, that high pressure. So what happens is that it expands. And so this is reflected by how you draw a turbine, which is now, well, the opposite of a compressor, right? So this is now your turbine. And again, we are dealing with steam, aka water, right? So now we will have here, right, a small cross-section and a big cross-section after. So we will have here your state 1, right, your state 1, and then your state 2, right? Your turbine has a pressure and temperature of 30 bar, 360 degrees Celsius, pressure and temperature of 30 bar, and then 360 degrees Celsius. I can smell that I don't need to mise en place this because, well, I kind of don't need a value of kilopascal. I will explain later, right? Or I will explain now. This to me just smells like my intuition tells me this is quite clearly a superheated vapor. And if we were talking about a superheated vapor, well, I don't need to look at this as in terms of kPa because, well, the thing is we only need these values for us to get certain other properties, right? So this is a superheated vapor and then it escapes as a saturated vapor. So in this case, even though your pressure 2 is already in kilopascals, which is 8 kPa, mind you, this is very small, you're going to have to turn this into a bar, right? Bars, which is 0.08 bar, right? Because you need to find other how do we say this? Other properties from here, okay? And so now, the turbine develops 8.95. By that, they mean that, oh, you are receiving power, right? 8.95 megawatts, or let's turn that into kilowatts so that we don't get confused, 8,950 kilowatts. And mind you, the unit is positive because work is being done by the turbine. The turbine is absorbing, or rather, the turbine is giving out 8,950 kilowatts worth of energy. Sadly, it just so happens also that heat leaks out. Heat leaks out at a rate of 0.586 megawatts, so negative 0.586 megawatts. Or, let's turn this into kilowatts, negative 586 kilowatts. Okay? And so now, I think everything is set. We can go into, what is required, right? Ang required ay how much steam is flowing to the turbine into, which means we should be looking at state 1. What is the volume flow rate at state 1? And basically, this just means that we need to know what your mass flow rate is and what the value of V1 is, which seems good enough for us, right? Because, well, state 1 is completely defined. We have a pressure and a temperature. You only need two thermodynamic properties to completely define the state, right? So we can get the value of V1. So actually, you know what? Let's bookmark that now. We need to get the value of V1. What else do we need? We need to get the value of m dot. How are we going to do that? We'll see, right? Let's just write down the first law. And that is how we will see. Q minus W is equal to delta KE plus delta PE plus delta H. And again, dot. I'll try to make sure to include the dots now. We have a value of Q and W. And do we see here a change? Or rather, neglecting kinetic and potential energy changes, that is already being said explicitly, so we can just remove them. Even though you see there is kind of an elevation difference between the two. It's just a symbolic kind of difference, right? So now we can simplify this into Q minus W is equal to delta H. The thing with delta H is that now you can see, oh, it's just m dot times H2 minus H1. So that means we have a value of this. We have a value of this. We don't have a value of this. And this is what exactly is needed for our answer, right? We need this, right? And we can find the values of H2 and H1 because both states here are actually completely defined, right? So we just need these three things, right? And this is the value of getting a game plan, right? So that you don't flip through your Steam tables twice because God knows how much time you have to do to where is that again? I come from a time where there were no bookmarks in my Steam tables. So now, I suppose what I'm saying is very outdated, but still, right? We go now to the superheated water vapor region. Table pala rather. 30 bar and 360 degrees Celsius, we get 30 bar, 360 degrees Celsius. We're supposed to get the values of V1 and H1. So for V1, that's going to be 0.0923. Actually, let's have that away. 0.0923. Tama ba? Yes. Meter cube per kilogram. And then for H1, we will have 3138.7 kilojoules per kilogram. And then for H2, we will go back to the saturation tables because it's a saturated vapor at 0.08 bar. I still can't believe that's so small. It's here though, okay? So now we will get the value of Hg in here, which is 2577 kilojoules per 2577 right? Kilojoules per kilogram. Now we have here our values of H2 and H1, and so we can just plug everything in. Your Q is negative 586 kilowatts, right? Your W is 8950. All of these guys are in kilowatts. And the thing is, your M in here, right, is in kilograms per second. Your H2 is 2577 minus your H1 3138.7. If you want, you can shift solve this. Or what I will do na lang is I'm old school. Kids these days. No, joke lang. Right? I will now just divide. Right? 586 minus 8950. And if you're wondering, why am I not putting in the units? It's because we already put in the units earlier here. Right? I don't need to repeat that. Right? 2577 minus 3138.7. And this should be in kilograms per second. Note that you might be scared. This cannot be a negative value. Even though this looks like a negative value here, this is also a negative value. So this will all cancel out. This will be a positive value. We will get, let me just see, negative 586 minus 8950 all over 2577 minus 3138.7. We will get 16.977. 16.977. I will not round that down yet because what we need is V/1, which I will need value of M.4. So 16.977 kilograms per second. Oops, kilograms per second. Actually, I'll just put it below here. Your V/1 is M dot times V1, which is 16.977 kilograms per second times your V1, which is 0.0923 cubic meters per kilogram. You can see, cancel. We will get a value of 1.5669. 1.5669 or 1.57 should do it. 1.57 cubic meters per second. This is our answer for number, what is this number? Number 5. And now I will blow my nose. Okay, there you go, right? Again, we just need to adopt this kind of mindset that like, okay, what do I need, right? What do I need and how do I get it, right? If you know how to get it, and you can learn to assemble them together, and also the backbone of everything is unit analysis. If you do everything correctly, you will get to your answer, right? Okay. And if you're wondering, this is quite large, 17 kilograms every second. Imagine pushing that much every second. This is completely fine because look at how big that turbine work is. 8.95 megawatts. That's a lot. That's a big number, right? So there you go. You might notice, again, I find this, I don't want to say I find it easy, but like, just look. The structure is predictable. Predictable is, I find the right word, right? Look, you're always going to put Q minus W equals KE plus PE plus H. Right? Always. Oh, sorry. There's nothing more after there. And you're always concerned about the values of H. If anything, the only weird thing is this, right? The pump. And even then, I will let you know that there are many red flags. There are many red herrings in here, right? when you say that the temperature remains the same, I'm not saying that you should treat this as an isothermal. Instead, what you should do is you should, well, just, what do you call this? Just have this kind of mindset that, okay, your change in enthalpy is just going to be volume flow rate times change in pressure, right? So that's going to be it. So number 5 is done. Now we go number 6. This is fun, even if I'm sick. Anyway. Now, refrigerant 134. Okay, there you go. Refrigerant 134A. You know what? Let's just continue underlining now. Refrigerant 134A, initially at -4 degrees Celsius and 20% dry, flowing at 7 meters per second, passes through an evaporator. Okay, now we're in the territory of heat exchangers. By the end of the process, it is fully dry. It is fully dry. It measures -4 degrees still. Supposing that the mass flow rate is known to be 0.10 kilograms per second, what is the diameter of the evaporator? Oh, okay. Interesting. All right. What is the diameter of the evaporator? And how fast is the fluid going at the exit? How fast exit? Right? Now, let's put in the numbers. Right? -4 degrees and 20% dry, flowing at 7 meters per second. You know what? Flowing at 7 meters per second, it measures 4 degrees still. Supposing the mass flow rate is known to be 0.10 kilograms per second, there you go. That is our full, what do you call this? That is our full annotation here, right? Of course, like if you guys try this out, like you're gonna have different annotations than mine, right? I mean, like I'm thinking, maybe you're gonna have to fill everything up with a color that's not necessary. I don't need this. It's just a way for you guys to. It's a way for me to help you guys think about these problems, right? Be more critical about what you're seeing, right? Now, as to the look, right? How you're supposed to draw an evaporator, it varies, right? By varies, it means like, for example, you can just do this and you can just label it's an evaporator, right? That can be completely okay, right? As long as you know what an evaporator really does, right? Some people do this thing, right? This is what an evaporator does. Basically, right? In your, I don't want to go too much into in depth into this. Like for example, this is your room, right? I don't have the air conditioner on, so that's okay, right? Let's say for example, this is the outside of my room. This is like the condo wall, and then that's just the sky. And it's the sky, and then there are birds, right? What happens is that if, right, I have an air conditioner here, usually the butt part, the condenser is sticking out of the room, right? What is facing the room is the evaporator. What is facing outside the room into the environment, into the outside, is the condenser, right? And basically what the evaporator does is that, well, for example, I'm here. The thing is, because I'm alive, I'm emitting heat, right? And for example, I'm using the computer, right? I'm using the computer. There's your CPU. The computer is also emitting heat because it's using up electricity, right? Other things like, I don't know, if I have a cat or something, they also emit heat because they're alive. And for example, I'm cooking. I'm doing a lot of things here, right? I'm cooking. So of course, the thing that I'm cooking and plus the stove and everything is emitting heat. That heat, if it remains trapped in my room, will make the room hot. So I'm doing this in depth. Okay, but what a computer, what an evaporator does is that it sucks in that heat, right? It sucks in that heat. And so it doesn't sound like it's doing a lot, but because it's sucking in heat, there's no longer a lot of heat in the room. By that I mean the evaporator is responsible for making your room feel cold because it's constantly absorbing heat. What happens is that, well, you no longer feel hot, right? You no longer feel hot. Where does that heat go, right? It gets tossed outside by the condenser. That is why, again, like once you, for example, if you do walk past a condenser, that fat part with a lot of like coils and wires and black stuff, and it feels hot because literally it's expelling heat to the outside, right? So basically, what an evaporator does is that it receives heat. That's it, right? It receives heat. Okay, there you go. Say a very complicated way to say that it receives heat. So let's just put in here evaporator, right? So something goes in, something goes out. So if you're thinking about this, right? If you're thinking about this the correct way, the thing that is flowing here is the refrigerant, R134A, right? Where is the refrigerant? It's not in this room. It's inside the machinery in here, right? And so that is what we're tracking currently. That is the system that we are trying to think about, right? And therefore, if you have in here a refrigerant that is not hot, well, you can bet in here it gets hot because you add heat to it, right? You add heat to it. These things go in, these things go out, right? And if you remember, right, initially your what do you call this? Your refrigerant 134A is at a temperature of -4 degrees Celsius. And as you can see, it's still -4 degrees Celsius once it goes out of the evaporator, right? By the end of the process, it's fully dry and measures 4 degrees, -4 degrees still. So you're thinking, this is isothermal? But no, it's not, because before it only used to be 20% dry, aka its quality at state 1 is 0.20. And by the end, the quality at state 2 is going to be 1 because it's now fully dry, aka it's now saturated vapor, right? So as you can see, it got energy, right? It got energy. Now, what we want, or sorry, the mass flow rate is known to be 0.1. Mass flow rate is known to be 0.1 kilograms per second. What we need now is letter A, the diameter of the evaporator, and letter B, how fast is the fluid going at the exit? So VEL2, right? In this case, I also forgot your VEL1 here is what again? 7 meters per second. There you go. Now we have everything we need, and now we can go ahead and begin. Right? The thing about this is that there is mention of diameter. There's mention of velocity. So therefore, what are we going to do? Right? Well, conservation of mass. Right? When we're talking about diameter, it's very obvious that we need area. And if you combine area and velocity, you're going to get volume flow rate. And even though that's not the thing that is conserved, what is conserved is the mass flow rate. So the mass flow rate is already given here. So that should give us a clear way into what we need to do. And before we do that, I will just go to the bathroom. I'll pause. Okay, I'm back. All right. Where were we? Where was I? Okay, right. Conservation of mass. There you go. Right. Conservation of mass suggests that your mass flow rate should be equal to the mass flow rate at state 1, which is also the mass flow rate at state 2. Right? Doesn't need to be said, kind of. Right? So that means that your mass flow rate, which is already given, should be equal to A1, VEL1 over V1. Right? And that should also be equal to A2, VEL2, and then all over V2. So now we have an idea. Oh, okay, I think I need these things. Right? And also, what's happening here is that, in this case, right, you already have a value of VEL1. You have a value of M dot, of course, and kind of what you can do is you can get the value of V1, right? You can get the value of V1 because now this is completely, what do you call this? This is completely defined, right? You have a temperature and you also have a quality, which means it's saturated. You know where it is. Therefore, you can find the area, and from there, you can find the diameter. And actually, you don't need to find the diameter immediately from here, but because I am your prof, I will do it my own way, which is just direct doing everything. The thing is, you don't have to do this. Again, you don't have to do this, but I want to because I think it's more efficient, even though it's kind of more, ano tawag dito? Even though it's kind of more taxing. But at some point, like I just deluded myself to think now, okay, maybe this is better, right? Your V1 can be found, and therefore you just need to be able to get to this value of D, right? And so, how do we find our value of V1? Well, let's put it here. Your value of V1 is going to be VF plus X times VG minus VF at, where is this? Negative 4 degrees Celsius. Okay. So in here, negative 4 degrees Celsius, let's go into, what is this? R134A, right? R134A. It's probably here. Is this R13? There you go. And now we go to the temperature table. We have negative 4. And we're just looking at VF and VG. 0.7644 divided by 1,000. 0.7644 divided by 1,000 plus 0.2 times VG is 0.0794. 0.0794 minus 0.7644 over 1,000. All of this should be in cubic meter per kilogram. Therefore, your value for V1, is going to be equal to, let me just compute this, 0.7644. Is that right? Yes. Okay. 0.7644 over 1,000. Oh, sorry. Plus 0.2 times 0.0794 minus 0.7644 divided by 1,000. That gives us a value of, I will do a lot of decimal places here, 0.01649. Just as a way for me to retain accuracy or precision, right? V1. And we might as well be able to find V2. V2 is very easy. I've already written it down because it's saturated vapor. That corresponds to a value of Vg, which is 0.0794 cubic meter per kilogram. And actually, now we have this as well, right? And now, how do we get our value of D2? Well, let's just rearrange everything, right? Let's put our V, our denominators on top, and let's put our numerators at the bottom. So this will be D squared is equal to M dot V1 all over pi over 4 vel 1. And because you want just the value of D, you can just square root everything, right? This now becomes, what is this? Square root of M, which is 0.10 kilograms per second. Your V1 is 0.01649 meter cube per kilogram. All over, right? What I do here for pi over 4, I just put this in the calculator. Instead of pi over 4, I put 0.25 pi, right? It's the same thing. And then your velocity is 7 meters per second. Let's just check if everything tracks, right? Kilograms per second over meter cube times meter cube per kilogram, cancel. All over meter per second. What you can do is that you can just flip, right? What you can do is just flip. Now it's second per meter. Right? Now it's second per meter, therefore you cancel. You will have meter squared, but you're going to put all of that inside a square root. That means that this is in fact a diameter in meters. So that's something we should not forget. Right? Something we should not forget. Now we put all of this into our calculator. Square root of 0.1 times 0.1649 all over 0.25 pi times 7. That will give us a value of 0.017319. 0.017319 or 32 meters. Right? And I'm putting a lot of decimal places because I know that it should be in cm. So if it's in cm, we go 1, 2, our diameter is 1 0.73 centimeters. There you go. Right? And now, right? And now we go to the next question, which is, what is the velocity at state 2? Well, if we now know, right? If we now know the diameter, right, which is this thing, 1.732, I will store that. Okay? If we now know the diameter, we can now compute the area. So again, let me rewrite all of this. Pi over 4 d squared vel2 over v2. We now know actually the value of v2. We also now know the value of d. We know the value of m dot, therefore we can find the value of vel2. Right? Vel2 now becomes, right? If we just separate everything again, right? Vel2 becomes, what is this? You rise, akyat, right? You turn the denominators up and then you turn the numerators down, right? M dot V2 all over pi over 4 d squared. The thing about an evaporator is that you might be wondering, what does that mean, right? The diameter of the evaporator before or after? The thing about these evaporators, these condensers, is that they're supposed to have constant diameter. I suppose that needs to be said, right? Note, heat exchangers normally have constant diameter. Normally have constant diameter. Constant diameter. And also another way to write down heat exchanger is HX. So if ever you do see this, I don't know, in your job in the future, you know it's a heat exchanger. Right? So let's go back here. Velocity, right? Your M is 0.1 kilograms per second. Your V2 in here is 0.0794 meter cube per kilogram. All over your pi over 4, your 0.25 pi. Again, this is how I write it down. And then we write down the meter value. We write down the meter value. Why? Because that is the SI unit. Right? That is the SI unit. So once we do this, right? Kilograms per second. Right? Kilograms per second. And then meter cube per kilogram. Cancel. All over meter squared. Right? All over meter squared. So all over meter squared. Cancel. You will have meter per second, which is correct. Right? Now, 0.0794 all over 0.25 pi times the answer earlier. We will have, is this right? 21.5, 0.01. Sorry. That was not the answer earlier. Should be a squared. 33. Right? 33. Oops. Where should we write this? It seems like, okay, there's still, right? There's still room. Vel2 is going to be 33.702 or just 33.7 meter per second. There you go. And if you're wondering, why is that very fast? Well, it's because it's a saturated vapor. It's a vapor, right? These gases are supposed to be more fast, right? If this already has some fluid or has some liquid in it and it's going at 7 meters per second, mind you, it's very fast. What is that? Like 20 kilometers per hour? 21-ish? No, 25-ish? So something like that, right? This one is going much faster because it's now all vapor, right? And so there you go. Those are your answers. And actually, let me blow my nose first. I think there should be a third question in here because this feels like it's just a recap for conservation of mass. So I guess Sir Calo meant it this way. I'm not sure, but try and see. I will challenge you guys. Try and see how much heat did the evaporator receive, right? That is my challenge now. How much heat did the evaporator receive in kilowatts, right? How much heat did they receive? So that's a good way for us uh to think about the first law, right? So go ahead, pause, right? Go ahead and pause because I will add this now at my own discretion, right? How much heat did the evaporator receive in kilowatts, right? This is the special content you get from watching me online, right? I will not do this in class, I think, because I don't think I have enough time, right? Go ahead and come back when you are done, right? Supposing you are done, welcome back, right? Let's see if you're correct. Let's write down your Q minus W is equal to change in KE plus change in PE plus change in H, right? Now, the thing with evaporators and most other heat exchangers is that, well, they're not supposed to move. They're not supposed to jiggle, to vibrate, to move, to rotate. So there will be no work, right? There will be no work. And the thing is, well, was there any mention of a change in altitude? Again, even though there seems to be a difference in height here, it's just symbolic, right? There was no change, therefore we just say, oh, there's nothing, right? Sadly, there are changes in speed, so we're going to have to think about that, but that's it, right? And so what will happen now is that we need to get two more additional values, because if we expand both of these, Q will be equal to 1/2, or rather, 1/2, or not 1/2, but m dot over 2000. If you remember, why is it 2000? Because it's 1/2 mv squared, but because this is in watts, we need to turn it into kilowatts. This will be vel2 squared minus vel1 squared plus m dot times h2 minus h1. We have a value of mass flow rate. We have both velocities already. The only thing we need now to compute our value of heat is the two enthalpies, H2 and H1, which is good enough because it's already here, right? So now we will go 44.75 and 244.9. You know what? I'll just put it here. Your H1 is going to be HF plus X1 times Hg minus Hf, which will now be equal to, what is HF again? 44.75 plus 0.2, it's 20% dry. Hg minus Hf, your Hg is 244.90. Minus Hf, that's 44.75. And therefore, you will have here your value of H1, which is 44.75 plus 0.2 times 244.9, minus 44.75, that will be 84.78. 84.78 kilojoules per kilogram. And your H2 is already here. That corresponds to your value of Hg, which is 244.90 kilojoules per kilogram. Now, we're supposed to have no fear, right? Everything in here is supposed to be in kilowatts already. 0.1 over 2000 times your velocity 2 is 33.70 squared minus 7 squared plus 0.1 times, what is this again? 244.90 minus 84.78. This should all bring us to a value of this should all bring us to a value of 0.1 over 2000 times 33.70 squared minus 7 squared plus 0.1, 244.90 minus 84.78. That will bring us to a total value of, that's still a lot of heat sucked in, right? That's going to be a total heat of 16.066 or 16.07 kilowatts. Okay? Just goes to show you how powerful refrigerants are. Right? There you go. This is your full additional, right? Additional, right? Additional question for number 6. Right? Okay? Okay. Right? We're going so far at a very good pace. Now we go to number 7. Right? Number 7. Okay. Now we're going to nozzle territory. Okay. Steam. You know what? Let's highlight. Let's already continue highlighting. Right? Steam interacts with a high temperature nozzle. A high temperature nozzle. Horizontal nozzle. Oh, very interesting keyword here, horizontal. Operating at steady state. Entering at 30 bar, 440 degrees Celsius with a velocity of 20 meters per second, and leaving at 10 bar, 240 degrees Celsius, the steam is known to have a mass flow rate of 0.75 kilograms per second. Supposing that the operation is adiabatic, how fast is the steam going at the exit? And how big are the inlet and the outlet? Right? How fast exit? Right? Sorry, I blew my nose. Okay. Let's go on ahead with our details, our numbers. 30 bar, 440 degrees Celsius, entering with a velocity of 20 meters per second, leaving at 10 bar, 240 degrees Celsius. The steam is known to have a mass flow rate of 0.75 kilograms per second. Right? And so now, how do we draw a nozzle? How we draw a nozzle is kind of like a compressor, but instead of just the lines here, right, what you actually do is you draw the whole thing, right? The whole thing. This is the nozzle, right? There you go. And you have state 1 in here. State 1 is at 30 bar, 440 degrees Celsius. 30 bar, 440 degrees Celsius. I can already smell that this is a superheated vapor, right? And so it's a horizontal nozzle. You can see it's horizontal, right? There you go. And it's interacting with steam or just water, right? We know that the velocity here is 20 meters per second. So in line with what a nozzle does, we expect that the velocity at state 2 should be higher, right? 20 meters per second. And at state 2, we know that this P2 will be 10 bar. 10 bar. T2 is what? 240? Yeah, 240 degrees Celsius. And then the mass flow rate for everything is supposed to be what again? 0.75 kilograms per second. We say also this is adiabatic, therefore there's no heat that comes out or in, right? 0. Right? Is that enough? I think that's enough. Yes. And what do we need? We need for letter A, how fast, tama ba? How fast is the steam going at the exit? That's Vel2. And how big are the inlet and the outlet? There you go. I finally sneezed. Right? So what we need for part A is the velocity at state 2. And what we need for letter B is the areas. Right? How big are the areas? How big is the inlet and the outlet? If I say in terms of cm squared, of course, it's going to be area. But if it's just in cm, I'm referring to the diameter. Okay? Let's be clear there. Okay? So next, right? What are we supposed to do? Well, immediately we're supposed to write down our first law. Right? Our first law, Q minus W is equal to delta KE plus delta PE plus delta H. The thing is, there was no heat to begin with. And this nozzle is supposed to have no work as well. This is not supposed to vibrate, jiggle, rotate, what have you, right? So what we only have is this right side, and there is supposed to be no potential energy because this is lying flat, right? This is not angled so that there is going to be an elevation difference. This is just going to lie flat. So in this case now, this will be our equation. And mind you, I will say this right now, I don't actually care about this. At the very least, when we're talking about the first law, I don't care about the mass flow rate. What do you mean? Right? Let's just try and what do you call this? Let's just try and what do you call this? Let's try and expand. Yeah, there you go. That's the word I was trying to look at. Right? If we expand your changes in kinetic energy, what you will get is m dot over 2000, right? Times vel2 squared minus vel1 squared plus m dot times h2 minus h1. As you can see, if you divide both sides by m dot, it doesn't matter, right? So actually, it doesn't matter how much mass is flowing in through and out of this nozzle. It just matters that, well, oh, sorry. It doesn't matter. The changes in velocity do not matter on the mass, right? Even though that kind of sounds unintuitive, counterintuitive, that's true. It's because the first law says so. Okay? And so now, what are we going to do? Right? We need to find the value of vel2 first. So if we can begin, let us, right? We need to find values of vel2 and a1 and a2. And you're wondering, wait a second, why did you write down the first law? Right? Why did you write down the first law? All we need are velocities and areas. Shouldn't this be solvable already with the conservation of mass? And now I will reflect that question back at you, right? Because, well, we'll see, right? We have a mass flow rate, which is now equal to A1 vel1 over V1. That mass flow rate is also going to be equal to A2 vel2 over V2. Now, mind you, for a nozzle, it's completely okay to change A1 and A2. Sorry, I blew my nose. Okay, it's completely okay that A1 and A2 have different values because, well, that's what a nozzle does, right? It's supposed to have bigger here, smaller here. And if you want to exchange that, that becomes a diffuser, right? So this A1 and A2 have completely no relationship to each other. So now let's try and understand what's going to happen. We have a value of m dot. We have a value of vel1. And we can find, because of P1 and T1, we can find the value of V1. Same thing goes for V2, right? We have a value of V2. Oops. We have a value of V2. We have a value of m dot. But we don't have values for A2 and vel2. So look at this. We don't have a value for this, or this. So what happens here, right? This sounds completely unsolvable, except for A1, of course. Right? A1 sounds solvable because, well, you already have everything else here except for A1. So let's go find V1 and V2 now, if ever, right? Your value of V1 here for 30 bar for 40 degrees Celsius should be in the 30 bar for 40. 30 bar 440. There you go. It's 1062. 1062 meter cube per kilogram. And now, I suppose I have to spoil the surprise, right? The thing about this is that now you can use the first law for you to be able to say, okay, right? We can find the values of V1 and V2, sure. That means we can also find the values of H2 and H1. Right? And as a result, if I know the value of vel1, I can find the value of vel2. So actually, this is something that you can find through the first law, which enables you to solve A2. That is why I've written down the first law. It's not because I'm trying to mislead you guys. It's because when a nozzle works, if ever it's losing energy, as you can see, right? It seems to be losing energy because it came from a really high pressure, high temperature kind of steam into a relatively lower pressure, lower temperature kind of steam. So you might be thinking, okay, where does that energy go? Right? That energy must go somewhere. And the thing is, I've restricted a lot of things already. This is supposed to be same potential energy, right? It's not just supposed to jump really high, no. There's no heat transfer into or out of this system, no. And it's not supposed to generate or give generate or receive any energy via work. So what else could it have been? That means that only kinetic energy is available to change. That's why you lose some energy via enthalpy so you can gain some energy from kinetic energy, right? And so now, all of that is to say that I don't want to go through multiple passes of the superheated tables, right? I will also now get the value of H1. H1 is going to be, what is that? 3321.5. 3321. Oops. 3321.5 kilojoules per kilogram. Okay? And now, same thing goes here. For P2 and T2, where should I put this? I suppose I should put this here. V2 is now going to be at, where is this? 10 bar 240, right? 10 bar to 40 degrees Celsius. That is going to be 0.2275. 0.2275 meter cube per kilogram. And then H2 is going to be 2920.4. 2920.4 kilojoules per kilogram. And so now, my advice to you guys is that whenever you're looking at a nozzle and a diffuser, it's very tempting to just go like, oh, it's just conservation of mass, right? But always remember that change in energy has to go somewhere. And usually that has to do with the change in kinetic energy, right? So if you're trading it for lower pressure, that must mean that you have higher speed, right? You will also learn about this in in fluid mechanics, but I'm not the prof there currently. So there you go, right? There you are. And let's just try and solve this first. This A1 first, right? Let's just move things around. You will see that A1 will be M dot V1 all over VEL1, right? Hopefully that is clear, right? You put this up, you put this down, and therefore you will have a value of, what is your M dot again? 0.75. 0.75 kilograms per second. Your V1 is 0.1062 meter cube per kilogram all over your VEL1, which is going to be 20 meters per second. We've done this before, right? We've done this before, and the unit should be in meters squared, right? Cancel, cancel, right? Cancel, cancel. You will have meter cube per meter, or cancel, cancel. You will have meter cubed, right? And so your A1 will now be, excuse me, your A1 will now be, let me compute for this, 0.75 times 0.1062 divided by 20 meters per second. That will give you 0.003985 meters squared. And I'm doing as much as I can to like get all of the decimal places in that the calculator is giving me. Why? Because we're going to turn this into centimeters squared. Centimeters squared. Square centimeter. There you go. Right? This is not square centimeter. In fact, what you need to do is, for 1 meter, you have 100 centimeters. You're going to apply that twice. So, cancel, 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 cancel. You will have centimeters squared now. And what you will need is to multiply 100 twice. AKA 1, 2, 3, 4. Now we know that your A1 is going to be 39.825 or 0.83 centimeters squared. This is your value of A1. Now we move on into the first law, right? First law. What is going to be your velocity at the exit? Well, we can just compute it by going here, right? And mind you, again, like at this point, we don't care about the mass flow rate. We only care about it in the sense of the conservation of mass, right? But in here, otherwise, what you can do is just, actually, let's remove this for now. Let's just have that later, right? What we're going to have is that if you multiply everything by 2,000, you're going to get 0 is equal to VEL2 squared minus VEL1 squared plus 2000 H2 minus H1. This is to highlight that they are very important, right? A small change in enthalpy is already a lot, right? And what do you need? You need the value of vel2. So I will just move everything here to the left, right? Vel2 squared is going to be equal to vel1 squared minus 2000 times H2 minus H1, right? Excuse me. Now, what will happen is you just want the value of vel2, so you're going to have to square root everything, right? And this should give you good this should give you good reason for you to believe that this vel2 has the same units as vel1. Look, right? You look at this, and supposing that everything in here is correct values, right? Has correct values. This is just m squared over s squared. So if you square root that, that should give you everything in meters per second, right? So now we will have vel2 is equal to, your vel1 is what again? 20 squared minus 2000 times, what is H2? H2 is this 2920.4 minus 3321.5. There you go. And that gives you a value of, let me just see. That gives you the value of 20 squared minus 2000 times 2920.4 minus 3321.5. You will get a value, oh my gosh. Wow, 895.879 or 88 meters per second. That is like faster than the speed of sound. Okay, sige. I mean, the point of a nozzle is to increase speed, right? And it seems like a lot of energy was lost, right? You're giving away your energy via enthalpy so that you can receive it via kinetic energy. What I'm saying is that you're less hot, but now you're more fast, right? The fluid is now less hot, but is now much more fast, right? And based on this, we can just go ahead and plug it back into m dot is equal to A2 vel2 over V2. And we're now supposed to get the value of A2, which is going to be, if we rearrange, m dot V2 over vel2, right? So what will happen is that we will have this again, right? And now we don't have to worry anymore about the values, right? The values are going to take care, the units are going to take care of themselves. A2 is going to be 0.75 times V2, which is, what is V2 again? Yeah, V2 is 0.2275. 0.2275 all over your vel2 is 895.88. My goodness. Right? This will turn into 0.75, 0.2275 all over my answer, which is now 0.000190455. So 1905, right? This is meters again. If you remember, how do we turn that into square centimeter? You're going to have to multiply 100 twice. 1, 2, 3, 4. Now, your A2 will have... Someone's moving their bed. Okay. Anyway, now this will be 1.905. Are you guys hearing that? I hope you're not hearing that. That's scary. 1.905 or 1.91 is kind of good enough as well. So as you can see, right, the change in area is drastic. Right? The change in area is drastic from about 40 to 2. Right? That is a massive change in your area. Right? There you go. That's your answer for number 7. Right? That's your answer for number 7. And now, let's go to our final one, which is the interesting one. Right? This one. Right? In an air conditioning system. Okay. I'll give myself a little break because I've been doing this non-stop. Or, well, I did have the bathroom break, so I wasn't doing this non-stop, but still. right? We go now to number 8, and this is an example of a mixing chamber, right? A mixing chamber. So I think we've done everything so far. We have a pipe, which was discussed before. We have had compressors and pumps, right? We have had turbines. We've had heat exchangers. We've had nozzles and diffusers, and we have mixing chambers. Oh, we don't have what do you call this? We don't have throttling devices. So I suppose I don't know. Should we get one from problem set 5? I think you guys can do throttling devices naman. Let me see. Problem sets. Ah. There's only one like little uh throttling device question in here. This one, right? So hopefully you guys do understand like what is going to happen in there. Actually, wait lang, sir. I think Sir Kalaw has a problem with the throttling device. I'm not sure. Well, let's not worry about that for now. Let's just worry about this in front of us currently. An air conditioning system's ductwork consists of outside air at 32 degrees Celsius, flowing at 3 meters per second and 0.95 cubic meters per second, being mixed with return room air at 24 degrees Celsius, flowing at 2 meters per second through a 1.2 meter diameter. That is large. Through a 1.2 meter diameter pipe. Is that right? Was I doing this prop? Okay. To create mixed air flowing at 2.5 meters per second. Suppose that Q, kinetic energy, and potential energy are zero, and that the common atmospheric pressure is at 1 bar. How hot is the mixed air, and how big is the diameter of the mixed air? Okay, so now this is like everything going in all at once. So if you guys remember, in topic 4 we have conservation of mass. So now this is kind of advanced problem. Oh, they're drilling. That is unfortunate. Wait, let me see if that registers. They stopped drilling. That is being registered. I'm so sorry for the people watching this. I will just try not to stop speaking so that you don't have to hear that thing. I'll get this closer to my face if ever. I hope they stopped. That's enough time for you to drill through a wall. Nope, they're drilling still. Okay. Anyway, an air conditioning system's ductwork. So let's just get this going. Ductwork. This is an example of a mixing chamber, and you're saying to yourself, wait, how is this a mixing chamber? I will just say literally, there's the word mixed, right? Sorry. It consists of outside air, so outside air at 32 degrees Celsius, flowing at 3 meters per second and 0.95 cubic meters per second, being mixed with return room air at 24 degrees, flowing at 2 meters per second through a 1.2 meter diameter pipe to create mixed air, flowing at 2.5 meters per second. The common atmospheric pressure is 1 bar. So now they're asking how hot is the mixed air. So how hot mixed air, right? How big diameter of the mixed air, right? And then let's go in with our numbers now. 32 degrees Celsius flowing at la la la, at 24 degrees Celsius flowing at la 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 la, right? And then mixed air flowing at 2.5 meters per second is the goal. Suppose that Q, K, E, and P, E are all zero. And now we have a very complicated, a very involved, shall we say, a very involved problem. Right? Number 8, maybe it's better if we just create a diagram. Right? Diagram, there you go. Right. There it is. Okay. Now, you have here outside air. You have here outside air. You know what? Let's just call that letter O. And then in here you have return air or room air. Let's call that R. And then we will have here mixed air. Mixed air, let's call that M. Right? And basically what happens is that this is an air conditioning system. Right? And an air conditioning system, its goal is to, well, maintain and condition the air that you're breathing and living in. Right? What it wants is, or rather, what we want in the Philippines is a low temperature kind of air, right? And what happens usually is that air conditioners can achieve this very easily, and they can achieve this so easily that sometimes the temperature of the air will be too low for us to be comfortable. Like I remember Sir Efren always says that he has either read or studied or published something wherein he found out that the thermal comfort level for people in the Philippines, living in the Philippines, is 24 degrees Celsius, right? At that point, it's not hot enough that you need to, like, I don't know, get an electric fan or something. And it's not cold enough that you need a jacket or a blanket for you to be able to work and live and study properly. Right? That is why I keep my air conditioner at 24 degrees Celsius instead of I'm preaching what Sir Efren is saying here. Instead of, like, when people are doing or are setting their thermostats for their air conditioners to be at 18. And then he says that, like, he makes fun with those people. He's saying that, like, oh, you turn your thermostats at 18 degrees, but now you throw on a blanket or a jacket just to keep comfortable. So he's saying it's kind of like somewhat counterproductive that, like, you are setting it lower than you feel comfortable, and then you throw on extra pieces of clothing so that you feel comfortable instead of just setting it at 24. Right? So anyway, right, this is very Philippines-ish. Actually, let's ask, hey Siri, how hot is it in Manila right now? It's 34 degrees Celsius, right? So outside air currently here is at 32 degrees Celsius. So it's going to be mixed with room air, which is currently at 24, let's say, right? And then it's to create mixed air flowing at some velocity, right? And the thing here is that 24 might even be cold enough for some people. I remember, or I know, every night it gets too chilly for me. And my room is at 24 degrees. So I feel like I'm more comfortable at, I don't know, 25 or 25 and a half degrees Celsius, right? But that's just me. Anyway, it's now enough of the discussion. Now we go into the actual problem, right? Let's just tabulate here everything, or not tabulate, just state in here everything that we know. Outside air is going at 32 degrees Celsius. The velocity of the outside air is what? 3 meters per second. And its volume flow rate is 0.95 meter cubed per second. And mind you, everything in here is in 1 bar, right? Everything is in 1 bar. And then your return room air is 24 degrees flowing at, so 24 degrees in here, flowing at vel R, which is 2 meters per second. 2 meters per second. Oh, sorry, 2 meters per second. And its diameter here is going to be 1.2 meters. So it's quite wide, right? And so now, right, your mixed air will be what? Mixed air should flow at 2.5 meters per second. That is all we know. 2.5 meters per second. And so now what we want is, what is the temperature, right? What is the temperature of the mixed air? And then what is the diameter for the mixed air, right? And when we're thinking about temperature now, that goes off of what we're only currently informed of. If you're at topic 4, welcome, right? But now this is no longer under the scope of conservation of mass, right? Because it's temperature. We need temperature, right? And so now what we're going to do here is, well, think about first the things we can understand, right? For now, let's just think about conservation of mass, right? 2 things go in, outside and room air go in, and then what comes out, it's mixed air. So M in is equal to M out, of course, right? What comes in? What comes in is outside air plus room air. So it becomes mixed air. Right? There you go. And now we don't even know the values of these things yet. Right? And so what are we going to do? Might as well, let's just try and track and see if everything, we can get everything. Right? This is going to be AO vel O over VO. And the thing about this is that we actually don't need AO vel O because we actually have V slash O over VO. And the thing about this is that this is air. Of course, I totally forgot to put this in here. This is air. And if we're dealing with air, everything needs to be in Kelvin. Or everything needs to be absolute, right? So instead of 1 bar, we should just say 100 kPa absolute. Right? 100 kPa absolute. Right? And so now this means that your V is equal to RT over P. So we can put all of this into PO VO over RTO. Plus your MR, where is your MR going to be? Well, it's still this one, right? It's still this one. So how are we going to do that? AR vel R over VR. Right? What is your AR going to be? Well, it's going to be, because it's a diameter we're talking about, that's now going to be a pi over 4 dr squared, vel r, all over VR, which now we can turn again into, RTR over PR. So again, I am making this way more complicated than it should be. So let's let it stay there for now. And then our MM is going to be vel M over VM. Right? And so what we can see right now is that we have, if we turn all of this, literally all of this, into a super complicated equation, this will be PO VO over RTO, right? Plus, again, PR, pi over 4, dr squared, vel R, all over RTR is equal to AM. I don't know what AM means, right? But PM, AM, vel M, right? All over, oh, you need the diameter, no? So I can actually turn this into pi over 4 dm squared vel M all over, right? RTM. So a lot, right? But at the very least, literally everything in here is already shown, right? And now, let's just remember, all of this has the same pressure, right? All of this has the same pressure, aka this, and this we already know. You also know the value of VO, and you also know the value of R because you're supposed to remember that, right? You have a value of TO and TR. You have a value of LR. You have a VLR. You have a value of DR. So now what remains is, what is the value of TM? I don't know I do know the value of VLM, and I don't know the value of DM as well. And so as you can see, you can completely solve for this. AKA, you can solve for the value of MO. You can also solve for the value of MR. The only thing you can't solve now is MM, but the thing is, you just know, you know already these two things, which is equal to your value of MM. So hopefully all of this tracks, right? All of this tracks. Basically, because you're able to solve the left side here, you at least have a value for your MM. Right? So now, right, what are we going to do now? Well, let's take this one step at a time. Let's try and calculate first MO and MR. Okay, let's try and first calculate MO and MR. So you guys see, this is a very involved kind of equation, right? So let's first start off with MO. Is going to be, from here, that's going to be PO V slash O over RTO, which is going to be 100 kPa absolute times your VO, which is 0.95 meter cube per second, all over your RT. The R of air is 0.2871 kilograms per, kilojoule per kilogram Kelvin. And then your TO is 32 plus 273.15. That gives you, what is this? 305. 305. Is that right? Yeah, 305.15 Kelvin. 305.15 Kelvin. And so now, what are we going to do? We can just get the value of MO immediately. So we're going to have 100 times 0.95 all over 0.2871 times 305.15. That will give us a value of 1.084. Right? 1.084368. So I'm trying to get as many decimal points as I can. 1.08368. 0.084368. So this will be 1.0844 for now. And then for your MR, where should we put MR? We should put MR here. Right? That's going to be PR and then pi over 4 pi over 4 d squared dr squared vel r all over rtr. So again, everything is 100 kPa. And then now we have 0.25 pi, right? And then your dr squared, where's your dr squared? This one, 1.2 m squared times vel r. Your vel r is 2 meters per second all over, again, 0.2871 kilojoules per kilogram Kelvin. And your TR, what is your TR? 24 plus 273.15. That gives you 297.15 Kelvin. Sorry, I'm too lazy to like convert it using my phone. There you go. And again, this should be in kilograms per second. Right? We've done this before. Right? We've done this before. So now, where should we go? Now, calculate this. 100 times 0.25 pi times 1.2 squared times 2 all over 0.2871. 0.2871 times 297.15. That gives you 2.651388. 2.651388. So 2.6514 kilograms per second. Right? Now, we have a value for the mixed air, right? Which is just the sum of these two, MO plus MR. So that will be 1.0844 plus 2.6514 is equal to 3.73. 3.735757. So 7358, right? Kilograms per second. Okay. Now, what is this all for, right? We are not even close to getting to where your TM is and what your DM is. So what are we going to do, right? It feels like we cannot solve for DM unless we solve for TM first. And we can't solve for TM first unless we get DM first. The thing is, the diameter will be locked talaga behind conservation of mass. You can't get it through any other means. However, when we're talking about temperature, we are also indirectly talking about energy, right? Earlier we were saying, where was that? That was the pump example, right? We were saying that because your temperatures are the same, this means that there's no change in internal energy. That means that That means that for here, the amount of temperature, the temperature reading that you had, the temperature measurement that you have is indicative of, well, your amount of energy. So in this case, now I will tell you guys about the first law. How does the first law occur here? Q minus W is equal to KE plus PE plus H. Dot, dot, and again, no Q, no KE, no PE. And the thing about this is that even if this is a duct, right, and even though we might hear those sounds from the vents that like it vibrates or something, there should be no work. You might be thinking, what is this? Right? What does this mean? The thing about this is that basically, you're not thinking of H2 minus H1. You're not supposed to think of H2 minus H1 because the thing about this is that where is your state 2 and where is your state 1? Right? Instead, when we're thinking about a change in enthalpy, we should think about H out minus H in. Right? H out minus H in. Right? H out minus H in. And now, once we see this occur, H in is equal to H out. That is basically the foundation for us to understand this problem. What they mean to say is that the amount of energy when you go in should still be the amount of energy that goes out. And so, what are the energies that go in? Well, you have an energy going in from the outside, you have an energy going in from the room, and you have an energy from the mixed air going out. Right? And so now, we will put in here all of your outside air times the H of outside air plus the M of the room air times the H of the the enthalpy of the room air is equal to the mixed times the H of the mixed. And you might be thinking, okay, where is the T? Right? Where is the T in here? Well, the T in here is going to come from the fact that, well, you are dealing with air, and air is an ideal gas. Right? That is why we were able to compute for M using PV over RT. Right? That is why we keep using R of air. That is why we are always in Kelvin. That is why we're always in absolute pressure. All of the H's in here are going to turn into CPT. CPT. And then this is going to be CPT. And now you look. All of the CPs of here, shown in here, are just of air. Cancel, cancel, cancel. And what happens now is that, well, you can see your MOTO plus MRTR is equal to MMTM. So this might look like it's a temperature balance kind of thing, pero there's an explanation to this. I don't want to go much into detail as to why. Sir Kalau has an explanation of that. And I suppose, you know what, I should put it here since like this is the last problem. If you're not willing to accept this, because if you look at the units, it's just kilograms per second times degrees Celsius. That does look kind of weird. I agree. Right? So what will happen is that we're supposed to understand that your MM is going to equal actually your MO plus your MR. HM. Okay, and then what? Right? Let's first backtrack. Let's first just explore this a little bit more. Right? Ito yung shortcut. This is the shortcut. Right? If you understand, well, now we're going to say that, excuse me. Okay, now we're going to say that we are now going to group these things in terms of the MO and the MR, right? We're now going to group them like this, right? And basically what will happen is that if I move everything to the left side, what will happen is that I will have MO times HO minus HM plus MR times HR minus HM. The thing now is that this, we are much more comfortable because you actually don't use, ito lalagay ko dito, note I'll put in here this note. You don't use H or U values alone, right? They are differences. They are differences. Differences with respect to what? Right? Differences with respect to some reference point. Right? Some reference point. I remember seeing some of that reference point be in your what do you call this? Tama, in your what do you call this? In your Steam table, I think it was R22. There is a reference point in here. Yeah, this one. Look, if you see R22 at negative 40 degrees Celsius, you will see that it is oddly all 0 for H and 0 for S, for entropy. And you might be thinking, oh, that's such a perfect material, right? It's such a perfect material to have that kind of property. The thing is, no, it was just made to be this way, right? It's just a standard because at this point, right, for some reason, either people from ASME or ASHRAE or what have you kind of standard institution just dictated that, all right, we will set R22, refrigerant 22 at negative 40 degrees Celsius to be our reference point. So if you're concluding from here, okay, if you use a value of 4.38, your value is actually just 4.38 higher than the reference point. If your value, for example, is 69.09, it's just going to be 69.09 higher than the reference point here. There's actually no parang absolute value. Unless you're talking about absolute zero, of course. There's no energy there because it's so cold that nothing moves. All of this is just going to be a reference. Right? And so suffice to say, this is actually how you should be thinking, how we should be thinking about our enthalpy and our energy. Right? It's supposed to only be a reference to something. Right? It's supposed to only be a reference for something. And now we can use MO CP TO minus TM plus MR, right? CP TR minus TM. 0. And now, again, you can cancel out your CP and CP, and they still should result in the same value. Right? Or rather, they should still result in the same answer. Right? It's just that this just plain looks wrong. This one is the more respectable version. But no matter which side you go into, I feel like that's fine. Right? I will prove it using this one first, and then this one after. Right? Let's try the shortcut first. Where should we put the shortcut? In here, right? Let's try the shortcut first. Your MO is 1.0844. And then your TO is, what is this? 32, right? 32. Now, your MR is 2.6514 times your TR. MR pala yun. Your TR is 24. Therefore, your mixed air is just 1 point, actually, it's here, right? 3.7358. 3.7358 times your TM. And now this looks very weird, and I will not put in the units because number one, they're all the same. It's just mass flow rate times temperature, and also, what is this, right? Kilograms per second times degrees Celsius. Sounds very wrong, but suffice to say, if you get your TM, it will be in the form of 1.0844 times 32 plus 2.6514 times 24 all over 3.7358. Now, based on the forbidden formula, 32, 24, you will get 26.32, right? Your TM in here will be 26.32 degrees Celsius. So this is your answer for TM, right? Let's try the long cut now. Right? The long method, by the way, right? So that's going to be MO 1.0844 times the CP of air. If you guys are not aware of the CP of air, you can calculate it right now, actually. You can calculate it right now. CP is going to be KR over K minus 1, right? That's going to be, for air, it's 1.4 times 0.2871 all over 1.4 minus 1. You will get a value of, let me just get this value. Oops. You'll get 1.00485, or might as well just say 1.005 kilojoule per kilogram Kelvin. So 1.005. Right, times your TO, which is 32, minus your TM, plus, right, your 2.6514 times, again, your 1.005 times your TR minus TM. Right? TR minus TM, 24 minus TM is equal to 0. And now, if you shift solve this, right, because I will shift solve this, now 1.0844, I'm not going to bother multiplying it by 1.005. It's already there. 32 minus x plus 2.6514 times 24 minus x is equal to 0. So your TM, again, will be 26.32 degrees Celsius. So even though the shortcut does look cursed, right? Even though it kind of is illegal, look at this, right? The thing is, the long cut agrees. So if you want to memorize this, go ahead. If you want to memorize this instead, then go ahead as well, right? So there you go. That's your value of TM. And now, finally, we can solve for our value of DM by here, right? We now have a value of of TM. And we have a value also for MM. So everything in here should work flawlessly, right? So I'm just going to rewrite it here. Your MM is now going to be PM, right? Pi over 4 DM squared vel M all over R DM. And so I will put all of the numerators above. I'll put all of the denominators above. I'll put all of the numerators below. And now we will have your DM, right? Your DM squared is going to be equal to MM R TM all over, right? All over PM times pi over 4 times times vel M. And now, for us to remove the square, we need to just square root, right? And so we'll plug this in now, right? Your MM is 3.7358. Your R is 0.2871. And then your T is, what did we say that was? 26.32. Plus, let's always remember, always in Kelvin, 273.15 all over your PM is always 100 in this case, times 0.25 pi, because I don't want to write down a fraction. And then the vel M is at what? 2.5. So if you put all of this together, your DM should be hold on, 3.7358 times 0.2871 times 26.32 plus 273.15 all over 100 times 0.25 pi times 2.5. That will give us a value of 1.2789. 1.2789 or 8998. So 1.279 meters. What is being asked in meters? So this is good enough. Or actually, if you want, you can also get this down to 1.28. Should be good. There you go. That is your value for DM. All this means to say is that this is a very involved kind of computation, right? This is a very involved kind of computation, but the underlying steps are very easy to understand, right? If you just look and zoom in here, oh, I get that, right? I get that. And then if you also zoom here now, oh, okay, yeah, that makes sense to me, right? No heat was added, no heat was removed, no work was added, no work was removed. Therefore, if you also include or if you also remove the changes in kinetic energy, which actually there are supposed to be also changes in kinetic energy in here because we have velocities, right? So that will add another layer of complexity to everything, literally everything, right? If you just narrow into these two values, right? If you narrow your vision into these two formulas, rather, conservation of mass and conservation of energy, you will see forward, right? Conservation of mass, which is this. And then here we have conservation of energy. So it's up to you guys if you want to include your kinetic energies in here, but they have specifically said that your change in kinetic energy is about zero, is negligible, right? So this is your full solution for number 8, right? This is your full solution for number 8. Actually, if we're limited to just these just like discussing these questions, I feel like for class I will just have to do pump work and then this one because it seems terrifying, no? Okay, so that's it. Thank you guys for watching. It would be a real pain if this had no audio. So let's just see if it does. Hopefully, yeah, my my voice is still in there. So thank you guys very much. Good luck with your studying. I know it's very intimidating, especially the last one. Pero if you keep practicing, this should be manageable. Okay. See you next time.